Okay, let's talk a little bit about datums. Datums are a standard reference point or reference ellipsoid used to determine position on the Earth. Reference ellipsoids, along with a network of carefully surveyed control points, establish a geodetic datum. Geodetic datums are standard reference points or reference ellipsoids that serve as a base for calculating positions on and above the surface of the Earth. You would need to survey a control point at the origin of a geodetic datum where the geoid and reference ellipsoid are perfectly aligned. All of the other survey points reference back to the origin. As the distance increases away from the origin, the surfaces between the geoid model and the reference ellipsoid model become separated, with the reference ellipsoid passing above and below the geoid. Because of this, different geodetic datums were developed for the best fit in different parts of the world. Some datums use the Earth's center of mass as the origin, and to accomplish this, satellite measurements calculate a position of the origin. So, for accuracy, geodesists calculate a position on Earth using two types of geodetic datums. We have horizontal and vertical geodetic datums. So, horizontal geodetic datums for the basis form the basis for computing horizontal locations, north, south, east, and west, and vertical geodetic datums are for the basis of computing elevation. So here are some common geodetic datums that you'll see. We have NAD in 1927, or North American Datum 1927, WGS 1984, which is pretty common. This is what Google Earth uses, and then NAD 1983. And so those first three are what you're going to see the most. We definitely use the NAD 83 a little bit more, but every once in a while NAD 27 comes around. And make sure that you are watching the videos in the text, because there will be a lot more detailed explanation of these datums in there. Around 150 BC, another Greek philosopher, Ptolemy, began to experiment with creating a grid of lines called a graticule to determine a position on Earth. A graticule is a network of parallels and meridians draped over a horizontal datum. Parallels are east-west lines that run parallel to the equator and are equally spaced above and below the equator. One measures the distance from one parallel to the next using degrees of latitude. Measurements start at the equator, which is 0 degrees latitude. From there, latitude continues north and south until it reaches 90 degrees at each pole. Meridians are a series of lines that run north-south and pass through the poles. The name comes from the Latin word for noon. One measures the distance from one meridian to the next using degrees of longitude. Historically, the origin of longitude was an arbitrary location, usually set by a cartographer's nation of origin. In 1884, the International Meridian Conference defined the international standard using the British prime meridian. The prime meridian is 0 degrees longitude, defined by the north-south axis of a telescope at the Royal Observatory in Greenwich, England. Longitude is measured east-west along the equator, starting at the prime meridian until it reaches 180 degrees in both directions. A great circle made from the circumference of a sphere divides the Earth into equal halves. The equator and every opposing pair of meridians form a great circle. However, a great circle can follow any direction as long as it divides the Earth into two equal halves. Great circles are frequently used in navigation since they represent the shortest distance from one point on Earth's surface to another. Even though Ptolemy did a great job in 150 BC, he was off a little bit. He thought that the circumference of the Earth was only 18,000 miles, but as we learned before, with Eratosthenes, they calculated it to around 25,000, and then we now know a more accurate 24 4,901 miles. The data we use in geographic information systems contain information about the location of real-world entities and phenomena. The features in our GIS are tied to real-world locations in the ground via these coordinates. We know where things are located on the ground because of these coordinates. Coordinates will be a part of a coordinate system, and there are hundreds of different types of coordinate systems. So again, locational information is recorded using coordinates, which define the location and geometry or shape of features in our GIS. And a coordinate system is a reference system used to define the locations of points in space. So we'll briefly go over the two types of coordinate systems. We'll get more into that next week, but we have geographic coordinate systems and projected coordinate systems. So geographic coordinate system uses angular measurements to define location on a three-dimensional ellipsoid, where a projected coordinate system defines locations on a flat surface using Cartesian coordinates of x and y, not using angular measurements, distance from the origin along the x and y axis. So basically, when you have a geographic coordinate system, this is what it is also included in that definition of datum. You are working with the sphere and the measurements based off of a sphere to be able to locate where you are on Earth. And it's three-dimensional, where you have your projected coordinate system, which is on a planar system. It's 2D or flat, essentially, and it's based off of x and y. It can go into the negatives as well, and so you'll see that when we get more into longitude and latitude and different types of coordinates, you'll see positive and negative numbers. And so one thing that's really important is that all projected coordinate systems are based off of a geographic coordinate system or datum, and all coordinate systems are based off of a datum. So basically what that means is that, and you'll see this more when you start working with projections, but a projected coordinate system is always going to have a geographic coordinate system or datum associated with it, where a geographic coordinate system will not always have a projected coordinate system associated with it. Latitude and longitude are measured by using a sexagesimal or base 60 system. Similar to units of time, one divides degrees of latitude and longitude into fractions of 60, so each degree consists of 60 minutes, and each minute consists of 60 seconds. The horizontal datum, the prime meridian, and the angular units of lat and long together form a geographic coordinate system. So why do we care? We need a common locational frame of reference so we can derive spatial information about the real world from our GIS. From an applied GIS perspective, what this means is that we need to get all of our layers into the same coordinate system. Data frame has to be in the same coordinate system as well before we start analyzing our data. If our data doesn't line up or everything isn't in the same system, our analysis results will be incorrect. One of the biggest problems you're likely to encounter, especially early on, is that your layers aren't going to line up. A rivers layer for Humboldt County here and a roads layer for Humboldt County there. Not always that obvious, and you may not even notice. And you'll start to understand this a little bit more later, but all the layers might be in universal transverse Mercator, but they're in a different datum. So they might be in one projected coordinate system, but they have a different geographic coordinate system associated with it. So it looks like everything lines up, but a small shift and your whole analysis and results could go wrong. Having a basic understanding of datums, coordinate systems, and map projections is necessary in order to use a GIS effectively. So let's go ahead and look at a couple of different examples here. So this layer of the Arcata Plaza is projected in the NAD 83 datum. And so this was an example of where the statue of McKinley is. Now we know that fortunately the statue of McKinley has been removed from the Arcata Plaza, but we'll still use it as the reference point, and we can also just say that it's the center of the plaza as well. But basically this is the center of the plaza. in NAD 83. And these are the coordinates that we have put into the GIS. And then if we were to put those same coordinates into the NAD 27 datum, you're going to come up with a different location. So it could really mean the difference between where you apply your project study. Another way to think of it is if I were to tell you that I buried some treasure under the statue or the center of the plaza and gave you coordinates but didn't give you the datum, you would be really confused and digging up holes where you shouldn't be. The difference here is about 30 meters. So you might not be able to tell if you were zoomed really out, but if you're zoomed up really close, it would make a huge difference. Another way to look at it is just to look at the coordinates itself. So here we have our degrees, minutes, and seconds set up in our latitude and longitude. And so you could see that that same point in time in the two different datums have different measurements for lat and long. So let's just go ahead and look at a couple of different coordinate systems laid on top of each other. So here we can tell that we do have a datum shift. So you can look for uniform offset. So here we have displayed NAD 83. It looks like a rivers layer of NAD 83 and NAD 27. And so you could see the same shape, but they're lined up a little bit differently because they're based off of different datums or geographic coordinate systems.